Turbocharger bearing systems are split into two main families: hydrodynamic bearings and ball bearings. In the previous training course, we saw how the oil flows through a normal hydrodynamic bearing system. We will now study in detail the two subfamilies of hydrodynamic bearing systems. Firstly, the fully floating bearing system has been used since Garrett turbos began production in the 1950s and are still widely used today. This uses two bearings with two oil films. An outer oil film between the bearing and center housing, which provides both stiffness and damping to control the motion of the rotor assembly and reduce the transmission of vibration and noise. The oil also passes through feed holes in the bearings themselves to provide an oil film between the bearing and the shaft. Due to the rotation of the shaft, the viscous oil is dragged in the direction of rotation, which also drags the bearing in the direction of rotation. So, the fully floating bearings rotate within the housing at around half the speed of the shaft. Secondly, the semi-floating bearing system. This design is preferred for our smaller, higher-speed turbos, which may rotate at over 300,000 RPM. These also have two oil films, but are prevented from rotating by an anti-rotation pin or locating pin. The outer oil film in this case is only providing stiffness and damping. Some of the oil passes through feed holes in the bearing and flows between the bearing and shaft. It is this inner oil film which provides the hydrodynamic support to the rotor assembly. The oil has the most important job to do inside the turbo: to support the high-speed rotor assembly and prevent contact between the wheels and housings. The movement of the rotor assembly is complex, and the constantly changing load on both turbine and compressor ends means that the oil must work hard. Therefore, high-quality oil is essential for the turbo. Viewing a section through a bearing system, notice that the shaft is not running exactly in the center, but due to the load, it is off-center and low. As the oil is dragged in the direction of rotation, it passes into a gradually reducing section, squeezing the oil hard and creating a wedge shape of very high pressure oil towards the bottom of the bearing system. The arrows show the distribution of pressure which is generated within the system. This high pressure oil film prevents the parts from coming into contact and controls the motion of the rotor assembly, avoiding any wheel-to-housing contact. When running at full load, the clearance between the shaft and the bearing are filled by an oil film which may be as thin as 7 microns, which is why clean oil is critically important to the operation and life of the turbo. The oil also feeds the thrust bearing assembly, which controls the axial motion of the rotor, flowing through feed holes in the thrust bearing to each thrust pad on both inboard and outboard sides of the bearing. The oil is dragged in the direction of rotation across each thrust pad, which has an angled ramp with a reducing wedge-shaped section, squeezing the oil hard and creating an area of high-pressure oil at the trailing edge of the thrust pad. This occurs on both sides of the thrust bearing, and as the load from the turbine or compressor varies, the oil compensates for this. As it is squeezed harder, the oil pressure increases and pushes back against the load. The thrust bearing system compensates for these constantly changing loads automatically up to its designed limit. The oil is working extremely hard in the thrust assembly, and under full load conditions, the oil temperature can increase by as much as 50 degrees Celsius as it travels just a few millimeters across each thrust pad. With such extreme demands on the bearing system, using the correct grade and type of well-filtered oil is critical to correct operation and a long operating life. The oil must also be changed at the recommended interval, along with a new OE quality oil filter. Failing to comply with these basic requirements brings a high risk of turbo damage from the single biggest killer of turbos: contaminated oil. There are many types of contamination which may be carried by the engine oil into the turbo bearing system and cause damage. The most common are fine particles, usually carbon from the combustion process. And if the concentration of these particles becomes too high, it acts as a very effective abrasive. gradually eroding and polishing the running surfaces of the bearing and shaft, increasing the clearances and closing up the oil feed holes until the oil is no longer able to control the shaft. This is usually accompanied by a sharp increase in noise level and oil leaking past the turbine end seal, causing oil to be burned and noticeable exhaust smoke. Oil may also leak past the compressor end seal and be blown into the compressor outlet pipework and charge air cooler. By the time this happens, the remaining life of the turbo may be extremely short because metal-to-metal contact will occur between the shaft, bearing, and housing, quickly followed by the turbine and compressor wheels contacting and rubbing on their housings. This causes wheel imbalance, leading to the shaft bending and often followed by fracture of the shaft. Catastrophic damage of this sort may lead to fragments of wheel passing into the air pipework, charge air cooler, and exhaust systems of the vehicle. Contaminated oil may also contain large particles, for example, fragments of metals from worn engine components, or even steel shot used for cleaning at engine overhauls. These should be trapped by an effective OE quality oil filter. But if the filter is of poor quality or is blocked and bypassing, these fragments may find their way into the turbo bearing system. Typically, this causes deep, irregular scoring to any or all of the following: shaft, bearings, housing, thrust pads, thrust collar and spacer. Scoring of the hard steel shaft cannot be caused purely by contact with the journal bearing, which is made from a much softer bronze material. So a scored shaft generally indicates contamination, with hard particles being carried in the oil. This scoring prevents the oil in the bearings from functioning correctly, and metal-to-metal contact occurs, followed by the same sequence of catastrophic damage seen previously. Our turbocharger warranty does not cover damage due to contaminated oil, which is mostly entirely preventable. Always check for any OE manufacturer's service bulletins relating to known problems with oil contamination for specific engines and vehicles and rectify the root cause. The root cause of damage to a turbo must be accurately diagnosed before fitting a replacement, or this may become damaged in the same way. The easy way to ensure that a new Garrett turbo will continue performing to OE standards throughout a long service life is to ensure that it always has top quality clean oil of the correct grade running through it.